Okay, so this is chapter 4. So chapter 3, we discuss. So basically, we are interested in finding right optimal DTR. So the definition. So there's a two-way. One is using the definition. Another one is using the result. So the result is this, right? So this is actually the result. I mean, this is sufficient condition. If we choose the option that maximizes this conditional expectation of the potential outcome over A, that turns out to be maximizing the value, right? So in that sense, so the result is what? Result is if one satisfies, right, then it is DTR, optimal. I mean, this one is optimal. So using this condition, we have two approaches. One is the Q learning, the other one is A learning. Using the definition of optimal. So the definition of optimal is actually different, right? We have a value function. So maybe we can use maximize the value over D. So that's another approach, which is the one that we're going to discuss soon. But anyway, that is the outline. But for the A learning, we have a very interesting result, which is called G estimation method. So I'd like to reflect this G estimation further and try to explain what is going on. So the point is, we basically want to make a joint modeling using some kind of a regression. So this is kind of a econometric style expression. So this is kind of convention that econometricians use for this kind of problem. So it's a model about the observation, right? So this is our data. X, A, and Y is our observation, right? Data. So we don't really introduce the potential outcome at all. We just use the model for the data, and then basically this joint density is a conditional times marginal, right? So this one is basically conditional. So this one is actually X and A, while this one is X, right? So this is conditional, and this one is marginal. Okay, and then this conditional. So these two error terms are independent, and also mean zero. And then the model specification is that our outcome model has a mean structure, has this kind of a semi-parametric model structure. By the way, the seminar speaker yesterday actually gives the very similar, right, framework. So this is basically the baseline, and this is our posterior drift model. I mean, in his terminology, the transfer learning terminology. So I found it very interesting because in the transfer learning, they call this model as a posterior drift model. So this is kind of posterior model, and then this is a baseline, right? So you have a baseline, and then so this is basically your Q, P and Q, right? In his, right? And then basically you have a two sample, P sample and Q sample, and then you want to kind of assume that they have something in common, right? Something in common in the baseline, but there's some additional, right? Additional systematic difference which he he want to model, right? Basically. So this is the kind of functional, non-functional form that gives the characterize the systematic difference. And then idea is if you using the sample P, you can compute P hat, whatever. And then basically use the current observation in sample Q, you can figure out a way, you have a way to estimate the parameter beta. But so that is a very similar context, but anyway, so I thought it's very interesting. But what is novel about this semi-pareto model approach estimation is that the James Robbins made a very clever idea of putting this A minus Q, which is the basically mean zero term, right? So expectation zero, by intentionally putting expectation zero term, he kind of make a extra protection, right? Extra protection. So basically, without this, right? Without this, you could just use the you could put A, right? And then solve this kind of equation. So you could actually solve this kind of equation. So this is naive. This could be called naive approach. You just use this approach, and because if your model, right? This is basically your regression model. So you have a regression model, and then basically you have this is a residual, and then you have some kind of covariate, right? To make the this equation, singular, I mean non-singular, so that you can have the unique solution. But interesting part is that you can, by making this one, you do some very interesting double protection. So that is I think that is why G estimation is so special and powerful. So that is basically connected with the Neumann orthogonality argument that we covered in the week 6 lecture, right? If you check the week 6 lecture note, I made a very rigorous description of the idea. But the point is that you basically you have a finite dimensional parameter of interest and infinite dimensional noises parameter, and you want to make it less critical, right? You want to make it less critical on the choice of the noises parameter. So that is the basically idea. So that means you want to make the expected value of the Gato derivative with respect to the noises parameter is 0. So that's what we want to show. Okay. So if this is true, then the condition of the Neumann orthogonality holds. So then we can apply the technique like sample split device method or parametric double robustness, right? So there's a two usage of this. Remember, there's a two usage of this condition. One is you can use a parametric model and argue that it is doubly robust and locally efficient, right? So that's one usage. Another usage is that you can if you use non-parametric machine learning model, then you need to do sample split, okay, sample split, and then argue this double devised machine learning argument. So basically, this is the estimated equation that we're going to use. So the only thing you want to check is this Neumann orthogonality. So the Neumann orthogonality is essentially checking this pass, right? so you have a line pass, and then you take the derivative with respect to T1 and T2, and then evaluate it and check that whether this is zero or not. And in this case, this is zero. So with respect to T1, this is, because this is zero, we use zero expectation. And then here we use zero expectation. So that basically shows that the Neumann observability holds, and so this G estimation method, it satisfies this double robustness. Sorry. Okay.
Okay, for your
Yeah.
first derivative,
Okay.
the first derivative, you take derivative with respect to T1, right?
Right.
With respect to T1, you have I minus I now. Okay. So, okay, so A cancel. Okay.
Right.
I see. A cancel.
Right. So yeah. So right. So pi null and nu null is true, but this is anything, right? And then you make it make, so basically this is kind of a somewhere between the two. Right.
The panel and the law only depend on X.
Right. Okay. Right. Pi null only depends on X. That's right. Okay. So that basically serves, so is gives some additional understanding of this A learning method. And another thing that may worthy of discussion is that, you know, the uncertainty, right? So this is estimation. So basically you will have to estimate, right? Eventually you will use the estimated C hat, which is basically, in this case, you will use theta hat, right? Theta hat to compute C hat X. So I kind of basically, in this case, there's a randomness, right? I mean, there's a, so whether, so in theory, right? So I guess one thing you may think about is, so we know that this is true, this is the best, but we never observe this one, right? Under the model, we only observe the estimated sequence. So there's a sampling error in it. So even though, so there's no guarantee. So even though this is the best, it does not necessarily mean that the C hat, right? The decision rule using plug-in C hat X is the best. There's no guarantee. So there's actually room for improvement. And if I understand correctly, there is actually the best rule is actually using some upper bound of the confidence interval. So it's not really this one. Actually, there's a way. So I think this is worthy of investigation, but we'll just move on for now. Okay, and now, so here's a additional alternative approach. So that instead of using the surface condition, right, using the result, or can you use the definition and apply it directly? Okay. So estimated value, I don't know why. Okay. Somehow, no. Okay. It's working. Yeah. So and this is particularly interesting, important, useful when we have a class of the decision. So instead of considering the whole class of the decision, suppose we have a particular parametric class, so that is a kind of subclass, and try to optimize among the class. And now we're going to view it as a classification problem. So that is a kind of interesting point. So I'd like to move on. So the classification is especially very popular in a machine learning area. So we have so Z is the label, and X is sometimes called feature, right? And then the idea is to minimize, to find the classifier that minimize the classification error. So classification error is basically if it's not correct, right? Then it so C and D are all binaries, either 0 and 1. So that's why. So this is either 0 and 1. This is either 0 and 1. So that means you have a Z and DX. You have a 4 choices: 1, 1, 1, 0, 0, 1, 0, 0. So then there's these two, no error, right? But those in the middle contributes to the error term, right? Error. Okay. And then sometimes we are particularly, we'll see that we're going to use weighted classification problem soon. Okay. And so let's consider 0-1 decision rule. And then recall that so this is estimated value for a given decision rule D, right? DX. And then this is IPW, augmented IPW estimator. So this part is IPW, the usual IPW. And then this one basically have a augmentation, right? And then augment the best one we project is basically condition expectation. So because everything is defined with respect to the potential outcome, I mean, in terms of A, so we need to rewrite it. So basically, delta D is the one indicator whether DX is consistent with A, right? So this is either 1, 1, then it's 1, or 0, 0 is 1. Otherwise, it's 0, right? And then pi hat XD. So basically, if it's about so A is A can be either 1 or 0. So if A equal 1, then we are computing the probability, estimate probability for A equal 1. For delta equal to 0, that means T equals 0, that means we are considering the estimating the probability of A equal 0 given X. So the same thing, right? This is basically this is basically we are kind of a QXA beta hat, and then I TX equal to A. So that's basically it's fine. And now, so I made a typo, so I just fix it. So this might be different from your slide, but I updated uploaded the updated one in Canvas. So basically, there's a lot of new concepts. So, but the point is that we have a value, right? Expected. So originally, this is potential outcome of the D, which is expected value potential outcome D, which is what so that is actually A Y star, because Y star is defined originally on A, and so you have a so so expectation of Y star D, which is expectation of summation of expectation of Y star A I dx t equal, we don't have to write, so indicator of the t equal A, right? A. So that is, but now we are talking about, so if you write this way, basically you can write it further as something like summation over A, and then expectation over the Y star A times indicator D equal to A, right? And then this one, you can write it. So this is basically parameter, mu A, right? So basically, if you write, so then all you have to do is, that means your estimated value should be estimator of, so mu A times indicator of D equal dx equal to A. Well, so actually I should write it. So this is an estimator, right? So that means you, to be more accurate, this is mu A. So that means dxi equal to A, and then you need to summation over and then you need to something like that, right? So that's basically this one, right? So if you compare this guy and this guy,
It should be mu half AI, right? It's also different.
that's right. That's right. Thank you. Thank you. Right. Thank you. So that's right. So this is not exactly true, but okay. So so how to, so let's okay. Yeah. Without this kind of question, I can finish the lecture very quickly. So it helps really to clarify and things like that. So I somehow last week I recorded the chapter 3 lecture. It ends quite quickly. Then so anyway, so this is not right. So as a concept, this is okay, but mu A itself is a when it comes to estimating mu A, right? Then you need to use the data. So how to fix it then? Well, Okay. So basically, I see. So basically, let's just so basically this is mu1 times so this is even this one is not exactly correct, right? Because d is dx.
D is DI.
So
I
so
think it's need to like derive from equation 4.
okay, thank you. Yeah, well, so I was kind of trying to derive from so okay. A y star a and then d okay dx is equal to a, right? And so and then you had d I guess so right so there's a several ways actually you can three ways using cube method, right? Outcome model using PS model. Third one is using augmented. So this is IPW. So this is AI augmented IPW method. So each one basically, for example, if you use outcome model, all you have to do, so this is, for example, outcome model, then you can actually write it as a QX1 I guess Q1. So my point is X and then yeah A. That is basically Q XA. Right. So that is actually it gives you something like right. That's for oops. Oops. That's for the outcome model. The same way you can do IPW. Then you basically use the different using the A. I guess there's no I actually at this point. Something like that, right? And then, so that gives you basically two, gives you something like actually this is not exactly correct. We need a indicator, right? And then so basically this one will give you
So also need the indicator of the D, EX and EX equal.
yeah, right. So where you are right. So this one should be actually Tx equal to A, right? And then this one that's the point, right? So then this one is actually pi so this one I had well, sorry, I kind of totally messed up because I should use the remember delta, right? So delta is basically dx equal to a, and then so let's just go back, try to reflect 3.2, I guess, right? This one. This is the as an this is optimal. Actually, even part 3 1 P1. So this is the outcome model, and then yeah, right. So this one, right? Okay. And so that basically gives you so the denominator, now we can see that this guy denominator actually has a summation, right? And the numerator is the same story. The numerator is actually this summation. Okay. So now let's go back to where we are. Yeah, from no, not this one. This one, I guess. Okay. So we don't have to repeat. And just so my point, okay. So now let's go just to try to make the not really. So I guess the point is basically this one. Okay, the equivalence. So the equivalence between 4 and 5 is simply understanding that even though it's all written as a kind of a summation, we actually it's either one of the two, right? One of the so as a d equal, okay. So we write it as a d equal 1 case and d equal 0 case. So d equal 1, dx equal to 1 case, which is dx equal to 1 case. We only care about the first number. So then this guy becomes a IA equal to 1. And then this one is a I. And then this one is a QX1. So that actually is this one. Same way, uh, now we're gonna write it as a so a equal 1, right? A equal 1, we have this one. A equals 0, basically, I'm sorry, not A equals 0. I mean, Tx equal to 0, right? Tx equal to 0. We are now talking about this term. We are considering this term. And so this guy can be plugged into here. This guy can be put into here and here. And then this guy is plugged into here. Okay. And then you get, after algebra, you get this. And now you can check, actually you can check that the expectation. So what you can check? You can check that the expected value of mu hat 1 A I P W is mu 1, and you can check mu hat 0 A I P W is mu 0. Either the outcome model or the propensity score model is true, right? So, for example, under the outcome model, A expectation of Y is just equal to this, right? So then that means you actually will have a cancellation, and the only thing left is this guy, third one. So pi divided by pi cancels, and so that is Q1, right? Same way for the expectation of the A, right? The PS second term will be 0 in expectation, and so this one will cancel. So that's you can get. Same thing here. You can check the same story, but you notice that you have a signs reverse because this guy is actually you have a, this guy is 1 minus A minus 1 minus pi, and then you have a minus. So you have a minus, and you are now using 1 minus A instead of A, and 1 minus pi instead of pi, and then 1 cancels, and minus cancels, so you get plus. So okay. So that basically gives you the final. So any basic, okay. So 5 is actually equal to this one. Why? Because this guy is dx is either 0 or 1, right? So indicator dx equal to 1 is equal to dx, because dx equal to 1 or 0, right? And so indicator dx okay, so my point is dx equal to 1 is, you can write it right. So because of the you can basically write it, use this one to plug into here, then write it as something like this. Okay. So that means all you have to do is so you are interested in maximizing this, right? So you are interested in maximizing this, but there's a maximizing this with respect to D. With respect to D. And so you can actually write it this way, and then this is a C hat. C hat is mu1 hat minus mu0 hat. So that is actually interesting because we call it what? What did we call this? Contrast function. Contrast. Remember the contrast function. So if I know the contrast function, then I know already what is the optimal DTR, right? Because this guy is simply just this one. But the only thing, maybe the one thing that is different is that we now allow this contrast function depends on y. Right? You have a dependency on y. So, but still, it's a contrast function because you are actually comparing the two. So your objective function to maximize is this one because so this guy is constant, right? You have a constant term here. So this is just you don't have to worry about. So all you have to do is to maximize this one. Given Ci hat. So we can write it as just a constant. And then there's a algebra you can apply. So so this guy, I in the last class I tried to show this, but usually this is not really easy. You should use this direction, right? From deep complex to simple rather than from simple to complex is more difficult. So anyway, so you can just try to simplify this. Okay. So first step to notice is that the indicators, squares of indicator function, it doesn't really make a difference. So you can just dx square is equal to dx. Indicator C is square is equal to the indicator, right? That's the first step. And then from second equation, it's just algebra, right? You just have the same thing, just to simplify, then you get second equality. From second to third, you have just another simple partition. So you partition one into two parts, right? And then do some algebra. Okay. And then you take dx, common dx to be outside. And then the only thing you're left with is this guy, which is actually equal to Ci. Because the absolute value, right? So if positive, then you just take the absolute value. If it's negative, then it takes the negative of the absolute value, which is original C, right? So that's kind of simple algebra, but end of the day, what we showed eventually is that this result. So given Ci, we are interested in finding Di that maximizes this, right? So that was the original problem, but we can reformulate it as this problem because the first term is constant. So you don't really have this is constant with respect to D. It's a free of D, right? So you, and then basically you maximizing this guy is minimizing the second term, right? Minus because of the minus. So then minimizing this one is kind of a loss function, right? You have a squared loss, weighted squared loss. You have a true label, and this is the function that you want to construct, find. And because this is a 0, 1, you can actually do some algebra to show that because this is easy, right? You have basically C indicator C. This guy is a true label. This is a classifier. So you have a 1 1 1 0 0 1 0 0, right? So the only thing this square matters is when we have this second and third, right? So that means the loss function. So as long as you can actually create a loss function that takes the value 1 only when these two arguments are different, is algebraically the same, right? So this in the context of this kind of classification, 0 1 classification, these two loss functions are equivalent. Okay. So the finding the optimal DTR problem can be formulated as a classical problem with a weighted loss function. So this guy is a label, true label, and dx is a classifier that you want to find, and ci is the weight. Okay, and the loss function is a natural 0 1 loss function. And and if you know the true contrast function, right? We know that if given the true contrast function, this is the global optimal DTR. So this is my point. That this guy is actually, you can write it as a T opt, right? This is the already best decision. And then this one is but this could be a function of y. So this is an optimal decision, but you want to approximate it by a function of x. And under the class that you are interested in, right? So basically, so the interpretation of this loss function is how much we can, right? So we want to basically reduce. We use the optimal one, global optimal one already. I mean, the best decision, and then we want to use approximation with the loss function as small as possible, right? And another observation I'd like to point out is that conceptually, the weight, right? So when it comes to finding the optimal DTR, what really matters is a large value of CI, right? So which kind of makes sense because you don't really. So suppose some element has a small difference, but some element has a big difference, right? Then you should focus on, in terms of developing the DTR, what you want to focus on is probably the one with the highest, right? Because that makes the big difference. I mean, you don't really care, right? Suppose you have okay, something like that. Then what you so this is, suppose this is C function, and then so this one you don't, okay, maybe I should make it more. Let's just make it like this. Okay, so this is C, and then basically the decision around this area is not really critical, right? The decision in this area, right, in this extreme case makes a difference. So in that sense, so this one will be negligible. I mean, so I don't really care, right? You don't really have to worry about this accuracy of this decision, but you should make sure that you have a good prediction. I mean classification in this area. Okay. Now, so that is the I think concept, important concept. And then when it comes to finding the classification function, usually in the machine learning literature, they use the concept of the decision function. So decision function is, so instead of trying to find the function D directly, they try to use estimate of F, and then use F as a use F to construct the D classifier, essentially.
So I want to ask a question.
Sure.
So suppose that for the third method we're talking about, suppose we do not care about the domain.
Mhm.
So then the optimal decision rule is just the indicator of say larger than 0.
You mean are you talking about this one or?
If you go to next page, I basically talk about the remark 1. So
Okay.
so if we do not care about the domain, right? So so basically you said that the optimization is within the domain D E type. Okay.
Okay.
So suppose we do not care about that, then the indicator of CI larger than 0 is the optimal rule. So then so on population level, they are the same as the G estimation and they are the same as the A learning and Q learning, right? So because A learning,
Okay.
learning
Right.
So on population level, but estimation will be different, right? So it's a 3 different ways.
Right.
So I'm thinking, I'm not sure whether anyone proved that if both the response model and the outcome model are correct, so this third approach and the A learning should be kind of asymptotic equivalent.
That's a good point. Right. So yeah, actually I wondered about that. But one thing I want to point out is here this C is actually function of Y2.
Right.
But in the G estimation,
There's no Y, right?
there's no Y, right? You see, C is, remember, so let's go back to, so in the G estimation, it's a function of X only.
Right, but G estimation also use the propensity score information, right? It's use A minus pi.
Right.
So if both modes are correct, because it's minimal solvable, right?
Right,
so
right.
it should also satisfy some optimality property in terms of estimation.
Right. So this one actually uses this model, right?
Right. But this model is correct if the outcome model is correct. And so
I see. Under this model, right?
Right, the outcome model is correct, right? So I'm thinking that the third approach is probably better if because it's doubly robust, right? So if the outcome model is not correct, but if the propensity score model is correct, so then the third approach is still right. But the A learning is not right.
I see.
Right. But if both models are correct, probably they kind of equivalent asymptotically.
Okay, right.
Yeah, I don't know, but
okay.
Yeah, I'm not sure whether anyone like a rigorous study.
Yeah. So basically, actually, I didn't cover it in my class, but in the book, the authors discussed that two approaches. So actually, we are talking about there's two approaches, right? Using this model, I mean, using this condition 1, and the other one is using the estimated value, right? And then question is under what conditions two approaches give the same answer.
Okay.
So actually in the book they discussed that, and one of the condition I remember is that when pi x, when it is purely randomized the design, when pi x is constant, they and pi x is constant, and then the model has a homogeneous variance, I mean the same equal variance, then two approaches are the same.
Okay,
Something like that.
Gives you exactly the same.
Right.
Okay.
Something like that. Yeah.
Yeah, but yeah.
Okay.
Anyway, to study the efficiency.
Yeah.
It's interesting. Probably.
Right. Yeah, I thought one thing I kind of impressed with this idea is that, you know, we statisticians usually care about estimation, right? We care about estimation, but we don't really care about decision much. The only thing we care about is hypothesis testing, right? Hypothesis testing is one particular decision, right? One particular decision given the criteria. But this is actually a good framework for decision, how you formulate your decision process from the data, right? Given you have a criteria. So that is actually very interesting framework to think about. And actually, if you, one thing I mean, this is a little bit not really well thought, but suppose you have a equals 0 and equal 1, right? I mean, your model, so you, even though the model says that you have a, but suppose you have a, so my point is that, so this is the expectation. So my question is this really always a good idea? Because you only care about the expectation. But so if you do that, then in terms of expectation, you know, choosing this decision one maybe seems to be better because it gives a higher expectation, right? But in terms of the risk, I mean, you may be worried about some. I mean, this one, suppose this one has a high variance. Then having the, so I don't know whether this, so suppose I'm worried about my objective function to maximize is a lower quantile, for example, quantile of y. So if y is kind of expected, y is kind of expected reward, right? But you, if we have a very high probability of being much poorer, much more riskier than doing nothing, right? Then is this still a good option? Right. I'm not sure. So right, something like that.
In portfolio allocation,
right?
So there is a mean and then there is risk, which is given by the variance, right?
Right.
So they kind of optimize like a combination of the mean and the variance. So
I think so. Yeah.
Like a quadratic.
I see.
Leader part and the
right. I see. So
probably something
right.
Formulated.
Right. So my point is, yeah. So my point is, even though we maybe this is good as a motivating, right? Start thinking formulating the problem. So maybe this is okay for now, using this value as a criteria to optimize, but that maybe is not really always the best thing to use, something like that. So let's move on. Okay. And so and then this is kind of problem is actually well studied in the machine learning classification literature. Yeah.
So I want to ask a related question about the meaning of the value function. The value function is expectation, right?
Expectation,
so
right?
Which means that I have a decision rule applied on a group of people, and then I just care about the expected.
Right.
Like
average,
right? Average,
right.
But if for some kind of individual people,
that's right.
People always think about how to make myself best.
Right.
Right. So then the decision rule for each people would be like, yeah. So not in terms of maximize this value function of average.
Yeah, right. But the actual decision is a function of x.
Right. The actual decision, but when we measure the outcome, it's not given x.
Right.
what is the
Right.
the value function is the average value function
That's right.
across all
Yeah,
the
right.
subjects.
So yeah, so this kind of problem is very interesting, but I don't have enough knowledge at this point. But anyway, so see this one. Basically, this is label, right? True label, and this is classifier. And our loss function is basically gives. So it gives a indicator value 1 only if they are different. So another way of writing this way is this way, right? You make it as a, so you change your label to plus minus 1. Right? It's either plus 1 or minus 1. And then multiply by the function, classify decision function. And then if the product, so the product is positive only when they are same sign, right? So F is plus and this guy is plus 1, then it gives 0. Right? So we want to give so this one, that's exactly same, right? Because this is my point. So this happens, this is equal to 1 only if C I and the C, okay, CI is positive and Fx is, so this is 1 only if Fx negative or CI is negative and Fx is positive, right? So that is actually same as this guy. So this guy is two indicator CI 0 minus 1 is equal to 1 and indicator. So basically we want these two product. So if these two product has a negative, then we'll get positive plus 1 here, right? So that is basically the idea. So which is kind of classification problem. So this kind of and then nice thing is you can actually write it is a one like a general, right? Unconstrained, like a linear model, or even you can write so linear model of X or some, or even you can make it reproducing corner Hilbert space theory. Then you can make it a linear function of the corner of the X, right? So span. So if you can actually span of the X in the sample. There's another way. So then this kind of optimization problem, we want to make a computationable. So then we need to some technique. So this 0-1 loss function is non-convex. So usually the idea is to change it by some hinge loss function and then you can do some computational advantage. Okay, let's move on to outcome weighted hour. So this is has a lot of citation. Is once close to 1,000 citations. So mostly very famous technique. So idea is suppose I now use the IPW estimator in the value function, value estimation. And then you can write it as something like this, same way, right? IPW, then this is basically IPW estimator of the y equal mu1, and this is IPW estimator of mu0. And then this is basically your, so using, once you write this way, you can write the cost function, right? I mean, this, not cost function, but the contrast function. So the contrast function has this form. And now, if y is binary, and y is a positive, non-negative. So y is usually the measurement, physical measurement of something, right? Blood pressure or something. Then this is positive, right? Usually. So in that case, you don't have to worry about this one. And then basically we care about whether this is right, this area. So this area is equivalent to, so when this is positive, so when y is, so you don't have to worry about y. But this is basically 0 and 1, right? A is 0 and 1. So this one is 1. So numerator is basically either 0 or 1, right? So if this is 0, 1 or 1, 0. So if it's 1, 0, then it's positive. If 0, 1, then it's a negative, right? So that basically means this is equivalent. So that means you can write this way. So then end of the day, you can write, okay. So end of the day, you can write the cost function, I mean the contrast function as this, and your indicator function, this one as a.
So in this method, the optimal one is not the indicator of CI not equal 0.
I'm sorry.
So in this method,
yeah,
the optimal one is not the indicator of CI not equal 0.
I see.
So in the previous one, the optimal one is the CI not equal 0, right? The indicator of CI not equal 0.
Well, I think so. The idea is, I think if I understand correctly, the idea is to construct it, to find the dx.
Right. So for the previous method, the D optimal is the indicator of CI not equal 0, right?
Okay.
So, but in this case, it's not.
Well, still. So this is contrast.
So then the optimal one is just AI. So there's no need to do the optimization, just
I see. That's the point. I see. So something's not really. So that's a good point.
So this CI is different from the previous CI, something like that, but
that's a very good point. I don't know. So this is not really the contrast function at all, right? Because you're right, this is not really. So the idea is we basically, this is all from the data, and using the data you can construct a wave, and then you just use the machine learning technique to construct a classifier. So that is basically the idea.
the median is similar. It looks like a contrast function.
So contrast. So I see. So I think the real contrast function is really this one, right? I mean, minus. So the by definition, the contrast function is a function of x only. So
Should not involve A.
so right. I mean, so it's a function of x only. This is the real definition of contrast function. And then using the contrast function to construct the indicator, right? Apply the indicator. That is the optimal, right? And so that part is only really the guaranteed one from the theory. So this is, so if we use this to construct the and then apply it to indicator, we get optimal DTR. But this one, yeah, so this one should not depend on A.
But the previous one is also depends on A.
Yeah, so that is, so I think so that means this is not really contrast. So we shouldn't call this one as contrast function at all. But if you use outcome model, right? So if, okay. So suppose I use outcome model only to construct the value we had, then we'll have only this one.
Right.
Then it is really the contrast function. Okay. But once you involve this indicator, then you mess up, right? You have a function of A and Y, then it's not really true. Okay. Okay. So I thought this is kind of interesting because basically the idea is to use to formulate the problem. So I think, yeah, so it gives a way how to formulate the DTR, optimal DTR problem as a classification problem. I thought that is an interesting part. But the actual computation, you need some understanding of how to do, right? How to find a function minimizing this. So usually you need a class, right, to find this kind of a function estimation. You need a class. So again, this kind of approach. So the issue, there's some issue of interpretability because interpretable DTR, we want to incorporate the domain subject matter knowledge. But if you purely use this machine learning type method, you can't, right? So there's a limitation. So this is attractive. This classification approach is attractive as it gives a flexible, and it can handle high dimensional patient information and achieve the good performance, prediction performance, because it's a machine learning approach, right? And but machine learning approach is a black box approach. So it lacks some scientific interpretation. So that is all for the lecture today, and this is basically for the single DTR, and then from this Thursday we'll move on to the multiple DTR where we have a multiple treatment.